Look up at the night sky tonight, and you're not just seeing stars, you're gazing into a time machine. Every flicker of light, every shimmering point in that vast darkness is a message from the distant past, traveling across unimaginable stretches of space and time to reach your eyes. Some of those photons began their journey before Earth even existed, racing through the cosmos for millions or even billions of years, carrying secrets about the birth of galaxies, the life cycles of stars, and the very fabric of the universe itself. Starlight isn't just beautiful, it's a beacon, a cosmic thread connecting us to events so ancient, so distant, they defy comprehension. Think about this for a moment. When you look at the constellation Orion, the light from its brightest star, Betelgeuse, left that giant sun around the time humans were first building cities. The photons hitting your retina tonight began their voyage when civilizations were in their infancy, and some of the faintest stars you see, their light may have started its journey before our planet had formed. That's the incredible power of starlight. It doesn't just illuminate the night, it carries echoes of the universe's history, preserved in waves of energy that cross the void. So how does this cosmic time travel work? How do photons, those tiny, weightless particles of light, survive such impossible journeys? What stories do they hold, and what can they teach us about the universe's grandest mysteries? In this video, we'll trace the epic voyage of starlight, from its fiery birth in the hearts of stars to its long, lonely trek across the expanding cosmos. We'll uncover how astronomers decode these ancient signals, using them to piece together the universe's past like detectives, solving a billion-year-old crime. And by the end, you'll never look at the night sky the same way again, because once you understand the journey of light, every star becomes a storyteller. To understand the ancient messages carried by starlight, we first have to unravel the nature of light itself. At its core, light is made up of photons, tiny, energetic packets that behave in ways that defy everyday intuition. These particles have no mass, yet they carry the electromagnetic force across the universe, moving at the ultimate speed limit of reality, 299,792,458 meters per second. But here's where it gets strange. Photons don't just act like particles, they also exhibit wave-like properties, creating interference patterns and bending around obstacles. This dual nature, known as wave-particle duality, baffled scientists for centuries until quantum mechanics revealed that light exists in this fluid, almost ghostly state between particle and wave. Every photon carries a fingerprint of its origin. When born in the nuclear furnaces of stars, they inherit specific energies based on the elements and conditions that forged them. A photon emitted by hydrogen, for example, tells a different story than one from helium or iron. Over time, as these photons race through space, they stretch or compress with the expansion of the universe, subtly shifting color like cosmic tape recordings played at different speeds. This is why astronomers can decode starlight by dissecting its wavelengths. They uncover the composition, temperature, and even motion of distant stars and galaxies. But how do these fragile messengers survive such epic journeys? Unlike ordinary matter, photons don't decay or age. Once set in motion, they persist indefinitely unless absorbed or scattered. Imagine a photon escaping a star's surface, dodging dust clouds and galactic magnetic fields, hurtling through eons of silence only to finally land in the lens of a telescope or the back of your eye. That moment of detection ends its billion-year voyage, converting its stored energy into a signal our brains or instruments can interpret. In this way, every glimpse of the night sky is a direct connection to the universe's distant past, written in the silent language of photons. Deep inside the heart of a star, where temperatures soar past 15 million degrees and pressures crush atoms together with unimaginable force, a spectacular transformation takes place. Here, in this seething cosmic furnace, hydrogen atoms collide with such violence that they overcome their natural repulsion and fuse into helium. This process, nuclear fusion, doesn't just create heavier elements, it unleashes torrents of pure energy in the form of photons. Each fusion event births countless particles of light, packing enough energy to power the star and eventually illuminate the cosmos. But escaping a star's core is no simple journey for these newborn photons. Picture a tiny particle of light bursting into existence amid a chaotic sea of superheated plasma. Immediately, it's absorbed by surrounding matter, only to be re-emitted moments later in a random direction. This cycle repeats over and over: absorbed, emitted, absorbed again, in a staggeringly slow dance that can last tens of thousands of years. A single photon might take longer to travel from the core to the star's surface than human civilization has existed on Earth. Eventually, after countless collisions, a photon reaches the star's outer layers, where the density thins enough for it to break free. With one final leap into the void, it begins its interstellar voyage, racing outward at the speed of light. But here's the astonishing part. The color and energy of that photon carry a hidden record of its birthplace. Hotter stars, like blue giants, produce higher energy photons, while cooler red stars emit lower energy light. Even the star's chemical composition leaves subtle fingerprints in the light spectrum, like a cosmic barcode waiting to be deciphered. Once liberated from its stellar cradle, the photon embarks on a journey that could span galaxies. It might traverse vast molecular clouds, skirt black holes, or pass through entire galaxy clusters, all while remaining unchanged, a perfect snapshot of conditions inside its parent star from eons ago. That's the miracle of Starlight. It's both a messenger and a time capsule, carrying pristine information across the ages. By the time it reaches our telescopes, that photon could be the last surviving witness to events that shaped the universe itself. The moment a photon breaks free from its star's seething core, it enters a gauntlet unlike anything we can experience here on Earth. Picture a single particle of light trying to navigate through an impossibly dense, churning ocean of superheated gas, where every fraction of a millimeter presents another obstacle. This chaotic journey, known as radiative diffusion, forces photons into a frenzied zigzag path, bouncing between atoms like a pinball in a cosmic arcade. Each collision absorbs the photon completely, only for it to be spat back out in a random new direction moments later. What should be a straight line dash to freedom becomes a marathon with countless detours. In stars like our Sun, this tortured escape route can take upwards of 50,000 years, meaning the sunlight warming your skin today actually began its struggle to escape around the time early humans were first mastering fire. For massive stars, where densities and temperatures soar even higher, the journey stretches far longer. Imagine a photon born during the last ice age finally bursting free into space today, carrying a message from an era when woolly mammoths still roamed the Earth. The critical turning point comes when photons reach the star's photosphere, that thin, glowing outer layer we recognize as the star's visible surface. Here, the density finally drops low enough for light to make its final break. It's a moment of extraordinary transformation. After millennia of chaotic motion, the photon suddenly finds itself racing unimpeded through the pristine vacuum of space. No more collisions, no more detours, just the open cosmic highway stretching ahead for light years. But this escape is only the prelude. The Photons' interstellar voyage brings new challenges, from threading through swirling dust clouds to bending around massive gravitational fields. Yet now, for the first time, it can truly race forward at its full, universe-defying speed, carrying not just energy, but a frozen moment from a star's ancient past, perfectly preserved across the eons. Once released into the void of space, a photon becomes the ultimate cosmic traveler, streaking through the darkness faster than anything else in the universe. At its blistering speed of 300,000 kilometers per second, it could circle Earth 7.5 times in the blink of an eye. But in the vast interstellar distances between stars, even light's incredible velocity feels sluggish. The nearest star system, Alpha Centauri, is so far away that its light takes over 4 years to reach us. And that's just our cosmic backyard. Photons from distant galaxies may spend millions of centuries in transit before finally meeting a telescope or a human eye. What's remarkable is how light defies the need for anything to push it forward. Unlike sound waves that require air or water to propagate, photons thrive in emptiness, their energy undiminished by the vacuum. They're like marathon runners who never tire, never slow, fueled purely by the explosive energy of their stellar birth. Yet even these perfect travelers aren't entirely immune to the universe's tricks. When passing near massive objects, galaxies, black holes, or galaxy clusters, a photon's straight-line path bends subtly, warped by the curvature of spacetime itself. Einstein called this effect gravitational lensing, and it transforms the cosmos into a hall of mirrors, where light from distant objects can appear distorted, magnified, or even duplicated by invisible cosmic lenses. Despite these detours, the photon's message remains uncorrupted. Every wavelength, every pulse of energy retains the precise signature imprinted upon it when it left its star. That's why astronomers treat starlight like cosmic Morse code. By analyzing its shifts and patterns, they can reconstruct not just where a star is, but how it's moving, what it's made of, and even how the fabric of space itself has stretched during the photon's epic voyage. The light from a single distant supernova, for instance, might reveal the universe's accelerating expansion, carrying clues about dark energy that no human instrument could detect directly. So the next time you see a star twinkling overhead, remember, you're witnessing the triumphant end of a journey that defies both time and distance. That tiny point of light has outrun gravity, dodged cosmic obstacles, and crossed unimaginable voids, all to deliver a story written in the language of physics, a story that began before pyramids were built, before continents shifted, perhaps before Earth itself existed. And if we know how to listen, these photons still have so much more to tell us. There's something fundamentally startling about the speed of light. It's not just a speed, but the speed, the cosmic rule written into the very fabric of reality. Einstein's theory of relativity revealed this astonishing truth. No matter how much energy you pour into an object with mass, it can never quite reach light speed. The closer it gets, the more its mass swells, requiring infinite energy just to inch nearer to that ultimate limit. Photons, however, cheat this system effortlessly. Born without mass, they hit the universe's maximum velocity the instant they burst into existence, like cosmic sprinters already at full stride. This speed limit isn't arbitrary, it's woven into the structure of spacetime itself. Imagine space as a vast, stretchy fabric, and light as a ripple racing across it. No ripple can outpace the tension of the fabric. It's the universe's built-in governor. This has mind-bending consequences. For example, if you could ride a beam of light, time would effectively stop for you. A photon crossing the cosmos doesn't experience its own journey from its perspective. Its trip across billions of light years happens in an instant. Meanwhile, for everyone else, that same journey unfolds over eons. This relativity of time and distance transforms astronomy into a form of archaeology. When the Hubble Space Telescope captures light from a galaxy 13 billion light-years away, it's not just seeing a far-off object, it's glimpsing a teenage universe, a snapshot frozen in light from when stars and galaxies were first taking shape. The longer light takes to reach us, the deeper we're peering into cosmic history. Even our own sun's light takes 8 minutes to arrive, meaning we always see it as it was 8 minutes ago. If it suddenly vanished, we wouldn't know until the last photons reached Earth, carrying the sun's final image like a delayed obituary. Yet light's speed, while staggering to us, is agonizingly slow on cosmic scales. The Milky Way alone is so vast that light takes 100,000 years to cross it. Entire civilizations could rise and fall in the time it takes a single photon to travel from one galactic spiral arm to another. This creates a paradox. The universe is old enough to have produced galaxies billions of light-years apart, but so enormous that much of it remains forever beyond our view. The light from the most distant objects hasn't had time to reach us yet, and some never will, as the expansion of space stretches the distance between us faster than light can bridge it. What makes light's speed even more extraordinary is how reliably constant it is. Unlike sound, which slows in water or speeds up in steel, light's velocity never wavers, whether it's passing through the vacuum of space or the heart of a diamond. This constancy lets astronomers use light as a universal ruler. By measuring how long it takes to reach us, they can calculate distances across the cosmos with astonishing precision. It's why we can say with confidence that the Andromeda Galaxy is 2.5 million light-years away, not because we've traveled there, but because its light has faithfully kept time on its marathon journey to our eyes. So the next time you flip on a light switch, consider this. The photons flooding your room are moving at the same invincible speed as starlight crossing the universe. They're part of the same unbreakable law that lets us unravel cosmic history, one luminous time capsule at a time, and every twinkle in the night sky is a reminder. We're not just observers of the universe, but participants in a grand, light-speed conversation spanning all of time and space. Crossing the cosmic void isn't as straightforward as it seems for a photon. Even in the emptiness of space, countless obstacles lie in wait. Thin clouds of hydrogen gas, microscopic dust grains, and energetic cosmic rays. These encounters transform a photon's journey into a high-stakes obstacle course, where every interaction leaves a mark. Some photons get absorbed entirely, their energy repurposed by atoms floating in the darkness. Others are deflected, sent careening off course like billiard balls in an interstellar pool hall. Take the majestic Orion Nebula, for instance. This stellar nursery glows with vivid pinks and blues, but those colors aren't just raw starlight. They're the result of photons wrestling with the nebula's thick molecular clouds. When high-energy ultraviolet light from young, hot stars slams into hydrogen atoms, it excites them like a cosmic game of hot potato. The atoms absorb that energy, only to release it moments later as visible light, specifically a crimson hue known as hydrogen alpha. Without these interactions, the nebula would remain invisible to our eyes, its secrets locked away in wavelengths we can't perceive. Dust, though far tinier than gas clouds, plays an equally dramatic role. Microscopic silicate and carbon grains, no larger than smoke particles, drift through galactic arms in vast tendrils. When starlight hits them, shorter blue wavelengths scatter more easily, the same effect that makes Earth's sky appear blue. This interstellar scattering explains why distant stars often look redder than they should. Like marathon runners coated in desert dust, their light arrives exhausted, stripped of its original vibrancy by trillions of tiny collisions along the way. Yet some photons cheat the system entirely. Certain wavelengths, like radio waves and infrared light, slip past these obstacles with ease, cutting through dust clouds like headlights through fog. That's why telescopes like the James Webb Space Telescope peer into the universe in infrared. It reveals hidden stellar nurseries and galaxy cores that visible light could never penetrate. Even cosmic rays, those high-energy particles streaking through space at nearly light speed, leave fingerprints when they collide with photons, subtly altering their polarization or trajectory. Astronomers don't just tolerate these distortions, they decode them. By studying how starlight changes during its journey, scientists reverse engineer the properties of the interstellar medium. A single dimmed star can reveal the density of a dust cloud light years away. A shifted wavelength might betray the presence of invisible magnetic fields twisting through space. It's like reading a letter that's been folded, stained, and slightly torn in transit. The imperfections tell their own story about the journey. Miraculously, most photons reach us relatively unscathed, their original messages still legible after eons of travel. That delicate balance between distortion and preservation is what makes starlight such a powerful tool. Every beam carries two histories, the ancient tale of its birth and the quieter saga of its passage through the darkness. And together, they paint a portrait of the universe far richer than either could alone. Here's where the magic of the Doppler effect transforms starlight into a cosmic speedometer. Picture a distant galaxy hurtling through space, its stars pumping out light in all directions. If that galaxy is moving toward us, its light waves get compressed like an accordion squeezed tight, shifting toward the blue end of the spectrum. But if it's racing away, those waves stretch out, reddening like a siren's pitch dropping as an ambulance speeds past. This same phenomenon, familiar from everyday sound waves, applies to light on an interstellar scale, turning color into a secret code for motion. What makes Redshift so revolutionary is how it fingerprints the universe's expansion. When Edwin Hubble first analyzed galaxy light in the 1920s, he noticed something bizarre. Nearly every spectrum he examined was skewed toward red. Not only were galaxies moving away from us, but the farther away they were, the faster they fled. This wasn't just random motion, it was as if space itself were stretching, carrying galaxies along like raisins in rising dough. That discovery became the first direct evidence for the Big Bang, proving our universe isn't static but dynamically evolving. Today, astronomers use redshift as a yardstick for cosmic distances. By measuring how much a galaxy's light has reddened, they can calculate both how far away it is and how fast it's receding. Some of the most distant galaxies we've observed have redshifts so extreme their ultraviolet light arrives as infrared, stretched by the expanding universe during its multi-billion-year journey. It's like receiving a letter where the ink has faded to another color, yet still deciphering every word perfectly. But redshift isn't just about expansion. Closer to home, subtle blueshifts betray the Milky Way's dance with Andromeda. Our neighboring galaxy isn't fleeing but rushing toward us, destined to collide in 4 billion years. Even stars within our galaxy exhibit tiny Doppler shifts, revealing their orbits around the galactic center or the tug of hidden planets. Each shift, whether red or blue, adds another brushstroke to our portrait of the cosmos in motion. a portrait painted not with pigments, but with the stretched and squeezed light of countless suns. Gazing at the Andromeda galaxy through a telescope isn't just observing another island of stars, it's opening a window to Earth's forgotten past. Those 2.5 million-year-old photons landing on your retina tonight began their journey when our ancestors were crafting the first stone tools, when woolly mammoths still roamed the frozen steppes. The light we see is a fossilized snapshot of Andromeda as it was before human civilization existed, preserved perfectly in its transit across the void. This time delay grows exponentially as we peer deeper into space. The brilliant spiral of the Whirlpool Galaxy appears to us as it looked 31 million years ago, an era when Earth's continents were unrecognizable, its dominant life forms vanished eons ago. Even more astonishing, the light from quasars at the universe's edge may have traveled for over 13 billion years, capturing moments from when galaxies were mere infants, still taking their first shape. Telescopes transform into time machines, their lenses collecting ancient light like archaeologists dusting off celestial artifacts, yet nothing compares to the ultimate time capsule, the cosmic microwave background. This faint afterglow, discovered accidentally in 1965, consists of photons released when the universe was just 380,000 years old. They've been traveling undisturbed for 13.8 billion years, cooling from searing gamma rays into gentle microwaves as space itself expanded around them. Studying this primordial light is like listening to the universe's first cry, a whisper from the dawn of everything. Its subtle temperature variations reveal the seeds of all future structure, the gravitational blueprints that would eventually grow into galaxies, stars, and planets. What makes these time-traveling photons so valuable is their unaltered truth. Unlike geological records on Earth, eroded by wind and water, Starlight arrives pristine, its message uncorrupted by the eons. When astronomers analyze the spectrum of an ancient quasar, they're reading chemical signatures from before our solar system formed. The absorption lines in its light, caused by intervening gas clouds, act like a cosmic barcode, detailing the universe's composition at different epochs. It's as if the universe kept meticulous photo albums across billions of years, and Starlight delivers them to our doorstep. This celestial archaeology reshapes our understanding of time itself. The night sky isn't a flat painting but a layered tapestry, where near and far blend with young and old. The bright star Vega shines as it was 25 years ago, while the somber glow of the Sombrero Galaxy shows us its face from 40 million years past. Every observation stitches together patches of cosmic history, allowing us to reconstruct the universe's story not from fossils or guesswork, but from first-hand light messages sent across the ages. The past isn't truly gone, it's racing toward us at light speed, waiting to be decoded. If Starlight could speak, it would tell stories in a language of wavelengths and energy signatures, each photon a tiny time capsule carrying encrypted data about its birthplace. Imagine catching a single particle of light from a star halfway across the galaxy and discovering it holds the chemical recipe of that star's atmosphere, locked in its spectral fingerprints. This isn't science fiction, it's how astronomers decode the universe. Every beam of starlight arrives with a built-in barcode, its unique pattern of dark absorption lines revealing which elements it passed through before reaching us. Hydrogen leaves a distinct signature, calcium another, iron yet another, like cosmic ingredients listed on a photon's passport. Take Sirius, the brightest star in our night sky. When its light passes through a spectrometer, the instrument doesn't just measure brightness, it dissects the light into a rainbow of colors, revealing dark lines where specific elements have absorbed certain wavelengths. These lines act as a stellar DNA test, showing Sirius's outer layers are rich in hydrogen and helium, with traces of heavier elements like oxygen and carbon. But here's the real magic. That same light also betrays Sirius's motion. If the star is moving toward us, its spectral lines shift slightly toward the blue end of the spectrum. If it's receding, they slide redward. This Doppler shift lets astronomers calculate not just what stars are made of, but how they're dancing through space. Supernovae take this cosmic storytelling to another level entirely. When a massive star explodes, it floods space with light so intense it can outshine entire galaxies. But embedded in that brilliance are telltale spectral lines, evidence of silicon, nickel, even gold forged in the stellar inferno. By studying these patterns, astronomers can reconstruct the explosion's mechanics, like detectives piecing together a crime scene from scattered evidence. The light from supernova 1987A, for instance, revealed the presence of radioactive nickel-56 decaying into cobalt, proof that these cataclysms are cosmic alchemists, transforming simple elements into heavier ones. Polarization adds yet another layer to the narrative. Some photons vibrate in specific orientations after scattering off interstellar dust or magnetic fields. This polarization acts like a compass needle, tracing invisible structures in space. When light from distant quasars passes through galaxy clusters, its polarization can map the cluster's magnetic fields, threads of force woven through the cosmos that no telescope could see directly. Even the afterglow of the Big Bang, the cosmic microwave background, carries polarization patterns that hint at gravitational waves from the universe's earliest moments. What's astonishing is how resilient these messages remain across incomprehensible distances. A photon from a quasar 10 billion light-years away retains traces of every gas cloud it traversed, each leaving absorption lines like footprints in sand. By reading these lines, astronomers can inventory the universe's missing matter, the elusive intergalactic medium that barely interacts with light except to steal specific wavelengths as photons pass through. It's as if Starlight collects receipts from every stop on its journey, allowing us to audit the cosmos's hidden ledger. This is why photons are more than just light. They're the universe's archivists, meticulously preserving snapshots of cosmic history in their quantum properties. From the temperature of a star's surface to the turbulence of its atmosphere, from the magnetic fields threading galaxies to the primordial echoes of creation itself, every photon is a page in a story that began billions of years before Earth existed. And with every telescope we build, we learn to read a little more of that story, written in the silent language of light. Modern telescopes don't just magnify distant objects, they open portals to bygone eras of the cosmos. When the Hubble Space Telescope captures an image of galaxy cluster MAX 0647, we're not seeing it as it exists today, but as it appeared 6.5 billion years ago, when our solar system was just a swirling cloud of gas and dust. The James Webb Space Telescope pushes this time-warping effect even further, detecting infrared light from galaxies like Jade's GC13, whose photons began their journey a mere 300 million years after the Big Bang. That's like uncovering a baby picture of the universe when it was only 2% of its current age. These cosmic time machines rely on a simple yet profound principle. The deeper we look into space, the further back we see in time. Every layer of the night sky represents a different epoch in cosmic history, like tree rings preserving Earth's climate record. But unlike archaeologists who piece together fragments of pottery or bone, Astronomers work with perfect, undegraded snapshots photons that have crossed billions of light years without losing their original information. The Hubble Ultra Deep Field, for instance, contains 10,000 galaxies spanning 13.2 billion years of cosmic evolution in a single frame, from mature spirals to primordial blobs of newborn stars. What makes these observations revolutionary is how they've rewritten our understanding of galactic childhood. Before Hubble, scientists debated whether galaxies formed slowly through mergers or emerged fully formed in the early universe. Now we know both scenarios play out. Webb's infrared eyes have spotted unexpectedly massive galaxies from the cosmic dawn, challenging theories about how quickly matter could clump together after the Big Bang. Some of these ancient galaxies appear more developed than our models predicted, like finding a toddler who could already compose symphonies. The secret to this time-traveling power lies in the telescope's ability to capture different wavelengths of light. Young galaxies recede so fast due to cosmic expansion that their ultraviolet light stretches into the infrared, invisible to our eyes, but perfectly detectable by Webb's gold-plated mirrors. It's like listening to a tape recording played at half speed. The song remains the same, just shifted into a lower register our ears can't naturally hear. By retuning our instruments to these redshifted frequencies, we effectively develop new senses capable of perceiving the universe's first starlight. Perhaps most astonishing is how these observations connect directly to our existence. The heavy elements in our bodies, the oxygen we breathe, the iron in our blood were forged in those early generations of stars, now visible only as faint infrared smudges. Telescopes like Webb aren't just showing us the past, they're revealing our own chemical ancestry, tracing how stardust from extinct stars eventually became the building blocks for planets and life. Each photon collected carries echoes of transformations that ultimately made our world possible. As these time-traveling observatories peer ever closer to the cosmic dawn, they approach a fundamental barrier. The era before any stars existed, when the universe was a dark, featureless sea of hydrogen. Beyond that lies the ultimate frontier, capturing the moment when the first photons broke free from the primordial plasma, the true first light of creation. With each technological leap, we're not just building better telescopes, we're constructing machines that can witness the universe's earliest memories before they fade into the endless expansion of space. Einstein's theory of general relativity didn't just redefine gravity, it turned the cosmos into a funhouse of mirrors where even light can't escape the pull of massive objects. Imagine a beam of starlight cruising through space, only to encounter a galaxy cluster so dense it warps the very fabric of spacetime around it. Instead of continuing straight, the light bends, curving around the cluster like a marble rolling along a stretched rubber sheet. This mesmerizing effect, gravitational lensing, transforms massive cosmic structures into natural telescopes, magnifying and distorting the light of galaxies so distant they'd otherwise be invisible to us. One of the most striking examples lies in galaxy cluster Able 168. Here, the combined gravity of hundreds of galaxies twists spacetime so dramatically that background galaxies appear smeared into luminous arcs like streetlights stretching in a rain-slicked window. Some even appear multiple times in the same image, their light split and redirected along different paths around the cluster's gravitational well. It's as if the universe itself is playing a game of cosmic peekaboo, revealing hidden objects by bending the rules of perception. Einstein predicted this phenomenon in 1915, but it wasn't until a solar eclipse in 1919 that scientists got their first proof. As the moon blocked the sun's glare, stars near the solar limb appeared subtly out of place, their light deflected by the sun's gravity, just as relativity had forecast. Today, we've scaled up that discovery to cosmic proportions. The Hubble Space Telescope's Frontier Fields project used lensing to detect galaxies over 13 billion light-years away, their light amplified by foreground clusters like a natural zoom lens. But gravitational lensing does more than just magnify. It exposes the invisible scaffolding of the universe. When astronomers map lensed galaxies, they often find the distortion is stronger than the visible mass of the foreground cluster can explain. The culprit, vast halos of dark matter, whose gravity tugs on light despite being utterly transparent to telescopes. By reverse engineering these distortions, scientists have charted dark matter's distribution across the cosmos, revealing how it weaves galaxies together in a web-like structure spanning billions of light-years. What's extraordinary is how lensing reveals multiple truths at once. A single warped image can disclose the mass of the lensing cluster, the distance of the background galaxy, and even the universe's expansion rate, all encoded in the light's detour. Some lenses act as natural time machines, too. The supernova Redshift appeared in 4 different positions around a galaxy cluster in 2015, its light taking separate routes that arrived years apart. Like a cosmic traffic jam, these staggered arrivals let astronomers witness the same explosion at multiple epochs, a quirk only possible because space-time itself had become a winding, twisted highway for light. From confirming relativity to unmasking dark matter, gravitational lensing proves that light's journey is anything but straightforward. Every curve, every magnified flicker in the night sky is a testament to Einstein's vision, a universe where gravity doesn't just move stars, but sculpts the very paths their light takes to reach us. And as our telescopes grow sharper, these celestial mirages will keep revealing secrets hidden in plain sight, written in the warped language of space-time itself. At the heart of light's strangeness lies a paradox that reshaped physics. Photons refuse to be just particles or just waves. They're both, switching between identities depending on how we observe them. The classic double-slit experiment lays this bare. When light passes through 2 narrow openings, it doesn't stream through like bullets or water. Instead, it creates an interference pattern, alternating bands of brightness and darkness as waves overlapping in a pond would. But here's the twist. If you place detectors to see which slit each photon travels through, the interference vanishes. The photons suddenly act like discrete particles, as if they're aware of being watched. This isn't just laboratory curiosity, it's the universe telling us reality depends on how we interrogate it. Even after crossing galaxies, photons carry this quantum mischief intact. Consider Starlight from the Whirlpool Galaxy, 31 million light-years away. Those photons spent eons racing through space, yet if we replicate the double-slit experiment with them, they'll still produce wave-like interference. It's as if their quantum nature is imprinted at birth, immune to the wear of time or distance. This resilience lets astronomers exploit wave properties to study cosmic phenomena, like using the flickering patterns of distant quasars to detect rogue planets or dark matter clumps through gravitational microlensing. The wave aspect becomes a precision tool, revealing details no particle behavior could uncover, yet light's particle side plays an equally vital role. When a photon from a supernova hits a telescope sensor, it deposits its energy in one precise location, a particle-like pinpoint. This allows instruments like the Hubble Space Telescope to build up images photon by photon, like a cosmic paint by numbers. The same quantum jumps that create spectral lines in starlight electrons, absorbing or emitting specific photon energies, depend entirely on light's particle identity. Without it, we'd have no way to decode the chemical makeup of stars or the redshift of galaxies. The implications ripple beyond astronomy. Quantum technologies harness this duality, with photons serving as qubits in quantum computers or secure carriers in quantum encryption. Even your smartphone's camera relies on photons behaving as particles when they strike its sensor. Yet light's wave nature enables fiber optic internet, where light pulses carry data through hair-thin glass threads. This duality isn't just academic, it powers our modern world while reminding us that the universe's deepest truths often defy everyday intuition. Perhaps most mind-bending is how this quantum split personality persists over cosmic scales. A photon emitted during the Cambrian explosion on Earth would still exhibit wave-particle duality today if intercepted by an alien astronomer. The universe seems hardwired to preserve this mystery, embedding it in every flicker of starlight. As we develop tools to probe further like quantum telescopes or space-based entanglement experiments, we're not just studying light's journey through space, but the very fabric of reality it illuminates along the way. What we perceive as visible light, the shimmering rainbow of colors from red to violet, is just a tiny sliver of photon possibilities. The full electromagnetic spectrum stretches far beyond what human eyes can detect, from radio waves longer than buildings to gamma rays smaller than atomic nuclei. Each type of photon acts like a specialized key, unlocking cosmic secrets invisible to ordinary telescopes. Take infrared light, for example. While our eyes see the Horsehead Nebula as a dark silhouette against bright gas, infrared telescopes like NASA Spitzer reveal its hidden structure, warm dust clouds glowing with newborn stars that visible light cannot penetrate. Similarly, the Chandra X-ray Observatory captures photons with millions of times more energy than visible light, exposing superheated matter spiraling into black holes or the million-degree remnants of supernova explosions. These high-energy photons originate in the universe's most violent events, where temperatures soar beyond human comprehension. At the opposite end, radio waves, the gentle giants of the spectrum, carry whispers from the coldest corners of space. The famous 21-centimeter line, emitted by cold hydrogen atoms drifting between stars, maps the Milky Way's hidden skeleton. Without radio astronomy, we'd never know about pulsars, those rapidly spinning neutron stars that beam lighthouse-like radio signals across galaxies, or detect the faint afterglow of the Big Bang itself, preserved as microwave static permeating all of space. What makes this spectral diversity so powerful is how different wavelengths complement each other. The iconic pillars of creation in the Eagle Nebula appear majestic in Hubble's visible light images, but switch to infrared, and the dense dust columns turn transparent, revealing hundreds of previously hidden stars forming inside. Combine X-ray, optical, and radio observations of galaxy clusters, and suddenly you're seeing three dimensions of reality simultaneously: the scorching intracluster gas, the glow of billions of stars, and the delicate radio filaments tracing magnetic fields woven through the cosmic web. Modern observatories have become masters of this full-spectrum approach. The James Webb Space Telescope's infrared vision peers through cosmic nurseries to witness planet formation in progress, while gamma-ray detectors like Fermi catch photons, packing enough energy to create matter itself. Each new window on the spectrum has rewritten astronomy. Ultraviolet light exposed the violent winds from massive stars. Submillimeter telescopes found the cold molecular clouds where complex organic molecules form, and even terahertz radiation reveals the mysterious, dark galaxies brimming with gas but few stars. This electromagnetic symphony transforms our understanding of cosmic processes. A supernova's story unfolds across the spectrum, first as gamma-ray flashes from radioactive decay, then X-rays from shock-heated ejecta, followed by visible light as the expanding shell cools, and eventually radio emissions as the blast wave plows through interstellar material. Without observing all these wavelengths, we'd miss entire chapters of the explosion's physics. The most profound revelation might be how ordinary visible light is in the grand scheme. Over 99% of all photons in the universe aren't visible to our eyes. They're infrared relics from stellar births, microwave whispers from the Big Bang, or X-ray shrieks from matter torn apart near black holes. By learning to see in these alien wavelengths, we don't just expand our vision, we step into an utterly new universe, one where darkness teems with invisible energy, and every wavelength tells a different part of the same cosmic story. The moment starlight enters a telescope, it carries more than just brightness, it holds a hidden language written in wavelengths. When passed through a prism or diffraction grating, that single beam fractures into a rainbow streaked with dark absorption lines and bright emission spikes. These patterns aren't random. They're the atomic signatures of elements like hydrogen, helium, and iron, each leaving distinct gaps or peaks in the spectrum as photons interact with electrons in a star's outer layers. It's as if every element in the universe has its own musical note, and spectroscopy is the instrument that lets astronomers hear that cosmic symphony. Consider our sun's spectrum, a vibrant rainbow interrupted by thousands of fine black lines, the darkest ones, called Fraunhofer lines after the 19th century scientist who mapped them, reveal hydrogen atoms in the sun's atmosphere absorbing specific wavelengths of light. Others betray traces of calcium, sodium, even gold elements forged in ancient stellar explosions long before our solar system existed. The same technique applied to distant stars uncovers their life stories. Blue giants like Rigel show strong helium lines, evidence of their youthful, high-energy fusion, while cooler red dwarfs like Proxima Centauri display molecular bands from titanium oxide, a compound that couldn't survive hotter stellar surfaces. But spectroscopy's power goes far beyond cataloging ingredients. When astronomers noticed the spectral lines of certain galaxies were systematically shifted toward the red end of the spectrum, they unlocked one of cosmology's greatest revelations: the universe is expanding. This redshift, caused by light waves stretching as space itself grows, allowed Edwin Hubble to calculate galaxy velocities and distances, laying the foundation for the Big Bang theory. Today, precise measurements of these shifts in supernova light reveal dark energies accelerating push on cosmic expansion, a discovery that earned the 2011 Nobel Prize in Physics. Exoplanet hunters wield spectroscopy like a forensic tool. As planets orbit their stars, their gravity causes subtle stellar wobbles detectable in spectral line shifts, a telltale Doppler wobble betraying unseen worlds. More remarkably, when a planet transits its star, some starlight filters through the planet's atmosphere, imprinting atmospheric chemistry onto the spectrum. The James Webb Space Telescope recently used this method to detect water vapor and carbon dioxide in exoplanet atmospheres, chemicals that could hint at habitable conditions. Future telescopes might even spot biosignatures like oxygen or methane, spectral fingerprints of alien life. Some of spectroscopy's most astonishing discoveries come from extreme environments. The spectrum of a neutron star's corona, for instance, shows iron atoms stretched into impossibly long lines by gravity, so intense it distorts space itself. Quasar light, after traversing billions of light years, arrives with absorption lines from intergalactic gas clouds, each a snapshot of the universe's evolving chemistry across cosmic time. Even the cold void between stars leaves its mark, as dust grains scatter blue light more than red, creating the diffuse interstellar bands that puzzle chemists to this day. What makes this science so revolutionary is its universality. The same quantum physics governing electrons in a lab on Earth applies to atoms in a star 100 trillion kilometers away. Whether analyzing the sun or a galaxy at the edge of the observable universe, spectroscopy translates light into a story of composition, motion, temperature, and history. It's how we learned stars are mostly hydrogen, that the universe is peppered with rogue planets, and that the fabric of reality is stretching faster every moment. Every photon's wavelength is a cipher waiting to be broken, and spectrographs are the keys to decoding the cosmos, one spectral line at a time. The hunt for extraterrestrial life begins not with spaceships or radio signals, but with the quiet analysis of starlight. Every photon that passes through an exoplanet's atmosphere carries subtle clues about what, or who, might exist there. When scientists point telescopes at distant worlds, they're not just looking for planets, they're searching for chemical fingerprints imprinted on light itself. Oxygen, methane, even industrial pollutants like chlorofluorocarbons could reveal the presence of life, whether microbial or intelligent. These biosignatures don't scream their existence. They whisper in the language of wavelengths, detectable only to those who know how to listen. Take Earth as an example. If alien astronomers analyzed sunlight filtering through our atmosphere, they'd spot unmistakable red flags of life. The simultaneous presence of oxygen and methane would puzzle them. These gases react quickly and shouldn't coexist unless something continuously replenishes them. That something, photosynthesizing plants and methane-belching microbes, this delicate imbalance, visible in our planet's spectrum, is what makes researchers so excited about finding similar patterns around other stars. When the James Webb Space Telescope studied exoplanet K218b, it detected potential traces of dimethyl sulfide, a molecule on Earth produced only by living organisms. While far from confirmed, such tantalizing hints show how starlight transforms into a cosmic detective's toolkit, but biosignatures are just the beginning. Technosignatures' evidence of advanced civilizations might hide in light's finer details. Artificial illumination on a planet's night side, for instance, would create unnatural brightness variations as it orbits. Laser pulses or structured light from distant stars could carry intentional messages. Even pollutants like nitrogen dioxide, a byproduct of combustion, might betray industrial activity. The Breakthrough Listen project scans millions of star systems not just for radio waves, but for unusual photon patterns that natural processes can't explain. The challenge lies in distinguishing true signals from cosmic false alarms. A lifeless planet with active volcanoes might mimic life by spewing methane. Young stars can bathe their planets in ultraviolet radiation that splits water vapor into oxygen, creating a false positive biosignature. That's why astronomers seek multiple lines of evidence, like the combination of oxygen, water vapor, and seasonal changes in vegetation like pigments. Upcoming telescopes like the Habitable Worlds Observatory will analyze dozens of Earth-sized exoplanets, comparing their spectra against exhaustive models of both living and sterile worlds. Perhaps the most profound realization is how recent this capability is. A century ago, we didn't know other stars had planets. Today, we're analyzing their atmospheres one photon at a time. Future instruments could spot city lights on distant worlds, or detect chlorophyll like pigments on alien continents, Every flicker of starlight holds possibilities not just for finding life, but for understanding our place in a universe that might be far more crowded than we ever imagined. Measuring the universe requires tools as vast as the cosmos itself, and nothing fits that description better than light itself. Astronomers have turned starlight into the ultimate measuring tape, stretching across billions of light years to map the unimaginable scales of space. The process starts relatively close to home with parallax, a method as simple as holding your thumb at arm's length and closing one eye at a time. As Earth orbits the Sun, nearby stars appear to shift against the more distant backdrop, a tiny angular change that, when measured precisely, reveals their distance. A star 1 parsec away, roughly 3.26 light-years, shifts by 1 arcsecond as our planet moves, its cosmic geometry on the smallest scales, but even this method fades into uselessness beyond a few thousand light-years, like trying to measure a mountain's height with a ruler. That's where cosmic lighthouses come in, stars with predictable brightness that serve as nature's distance markers. Cepheid variables, for instance, pulse rhythmically like clockwork, growing brighter and dimmer over days or weeks. The key discovery came from Henrietta Swan Leavitt in 1912. The longer a Cepheid's pulsation period, the greater its true luminosity. By comparing how bright these stars should appear up close to how faint they actually look from Earth, astronomers can calculate their distance with astonishing precision. It's like knowing a 100-watt bulb should shine at a certain brightness, so if you see one glowing dimly from far off, you can work out exactly how far away it must be. These stellar yardsticks helped Edwin Hubble prove the Andromeda Galaxy wasn't just a nebula, but an island universe millions of light-years away, shattering humanity's preconception of the Milky Way's solitary grandeur. For even greater distances, astronomers turn to the universe's most violent explosions, Type Ia supernova. These stellar detonations occur when white dwarf stars steal enough mass from a companion to trigger a runaway nuclear explosion, always with the same peak brightness, outshining entire galaxies. Spotting one of these cosmic beacons halfway across the observable universe lets scientists gauge distances so vast they defy intuition. In the 1990s, observations of these supernovae led to the spine-chilling discovery that the universe's expansion is accelerating, driven by some unseen force we now call dark energy. Without the consistency of starlight, both from living stars like Cepheids and dying stars like supernovae, we'd never have uncovered this fundamental truth about reality's fabric. The final piece of the cosmic distance ladder relies on light's stretching wavelength's redshift. As the universe expands, it stretches photons traveling through space, shifting their color toward the red end of the spectrum. More distant galaxies recede faster, showing greater redshift, a relationship codified in Hubble's law. By measuring how much a galaxy's light has reddened, astronomers can calculate its velocity and thus its distance. This technique has mapped the large-scale structure of the cosmos, revealing filamentary walls of galaxies separated by voids so enormous they make the Milky Way seem like a speck of dust. Together, these methods, parallax, standard candles, and redshift, form an interconnected chain stretching from nearby stars to the edge of the observable universe. Each rung builds on the last, cross-checked and calibrated until the whole cosmos snaps into focus, and at every step, light is the common thread, a messenger carrying not just stories of stellar lives and deaths, but the very coordinates of reality itself. The next time you gaze at the night sky, remember, every twinkle is part of an intricate celestial map, written in photons and decoded by those who know how to listen. For every photon that survives its epic journey across the cosmos, countless others meet untimely ends, vanishing into the darkness as if they never existed. Interstellar space might seem empty, but it's filled with obstacles that can derail a photon's voyage. Dust grains, no larger than smoke particles, lurk in vast clouds, absorbing shorter blue wavelengths like cosmic sponges while letting redder light slip past. Hydrogen gas scatters photons in random directions, sending them off course like pinballs in a galactic arcade. And in the chaotic hearts of nebulas, dense plasma can swallow light entirely, converting its energy into heat that fuels new generations of stars. These cosmic filters explain why distant objects often appear reddened. Their blue light has been stripped away, leaving only the longest wavelengths to complete the journey. The photons that do reach Earth face one final challenge: detection. Modern telescopes act as photon traps, their mirrors and lenses funneling starlight onto sensors no wider than a postage stamp. Charge-coupled devices, or CCD, have revolutionized astronomy by doing what the human eye cannot, counting individual photons with near-perfect efficiency. Each photon that strikes a CCD liberates an electron, creating a tiny electrical signal that computers tally like cosmic accountants. The faintest galaxy's Hubble has imaged required collecting just a handful of photons per minute, stretched over weeks of exposure. It's a staggering feat, capturing whispers of light that traveled billions of years, then amplifying them into something we can see, but raw detection is only half the battle. Astronomers must also untangle the distortions starlight accumulates en route. Interstellar dust doesn't just dim light, it polarizes it, twisting photons into specific orientations that betray magnetic fields threading through space. Gas clouds imprint absorption lines on spectra, revealing their chemical fingerprints. Even Earth's atmosphere poses problems, bending and blurring starlight like a funhouse mirror. Adaptive optics systems now combat this by deforming telescope mirrors thousands of times per second, canceling out atmospheric turbulence in real time. These corrections are why modern ground-based telescopes can sometimes outperform Hubble, capturing crisper images despite peering through miles of churning air. What makes this photon hunt so extraordinary is the sheer improbability of success. Consider the Hubble Extreme Deep Field, that iconic image of thousands of galaxies required collecting photons so sparse. The entire exposure gathered less energy than a single snowflake hitting the ground. Or gravitational wave events, where astronomers scramble to catch the fleeting glow of colliding neutron stars, sometimes with just minutes to point telescopes before the light fades forever. Every observation is a race against time, noise, and the universe's indifference. Yet when everything aligns, when photons survive their odyssey, when telescopes capture them flawlessly, when computers decode their hidden messages, we gain more than pretty pictures. We unlock the universe's history, written in a language only light can speak. Those streaks and smudges in deep field images aren't just distant galaxies. They're time capsules from epochs when stars burned brighter, when galaxies crashed together more violently, when the cosmos looked utterly unlike it does today. And with every technological leap, we're not just improving our ability to collect photons, we're refining our capacity to listen to the stories they've carried across the ages. Imagine standing on a hilltop a century ago, gazing up at a night sky so vivid the Milky Way cast shadows on the ground. Today, that experience is vanishing beneath the orange glow of streetlights and skyscrapers. Light pollution, the artificial brightening of the night sky, has erased stars from view for nearly 80% of humanity. In major cities, Fewer than a dozen stars pierce the haze where thousands once dazzled. This isn't just an inconvenience for stargazers. It's severing our most ancient connection to the cosmos. The consequences ripple far beyond astronomy. Sea turtle hatchlings instinctively crawl toward the moonlit ocean, but coastal developments disorient them with artificial lights, leading thousands astray each year. Migratory birds, navigating by starlight for millennia, collide with illuminated towers in shocking numbers. Even trees and insects feel the disruption. Some species bud prematurely under constant artificial light, while others abandon nighttime pollination as if perpetual daylight has rewired their ecological clocks. Humans aren't immune either. Studies link excessive nighttime light exposure to sleep disorders, depression, and even increased cancer risks. As our circadian rhythms fine-tuned over millennia to Earth's natural light cycles struggle under endless electric twilight. Yet solutions are emerging. Dark sky reserves, like Utah's Capitol Reef or Namibia's Namib Rand, enforce strict lighting controls to preserve pristine night skies. These sanctuaries aren't just for astronomers, they're proving grounds for lighting reforms that balance safety with sustainability. Smart LED systems, for instance, now use warm-colored bulbs shielded to direct light downward instead of skyward, reducing glare while cutting energy use by half. Flagstaff, Arizona, the world's first international dark sky city, demonstrates how urban areas can coexist with starry skies through intelligent design. Their streetlights, adapted since the 1950s, preserve views of Lowell Observatory where Pluto was discovered, while keeping streets safely lit. The battle extends to space itself. Satellite megaconstellations like SpaceX's Starlink reflect sunlight back to Earth, creating artificial moving stars that interfere with telescope observations. Astronomers and engineers now collaborate on solutions, from satellite sunshades to algorithms that remove streaks from astronomical images. Even ordinary citizens contribute through apps like Globe at Night, which crowdsource global light pollution data by asking users to count visible stars. Preserving natural darkness isn't about rejecting progress. It's about remembering that starlight shaped human culture long before electric bulbs existed. Cave paintings tracked lunar cycles, Polynesians navigated by star compasses, and Galileo's telescope revealed cosmic truths because Renaissance skies were dark enough to let him see. Today's children, if never shown the Milky Way, might grow up thinking the universe is small enough to fit between city lights. By reclaiming the night, we're not just protecting science or ecosystems. We're safeguarding wonder itself, ensuring future generations can still look up and feel the awe that sparked every civilization's first questions about the cosmos. The most hopeful lesson comes from places like the Italian island of Sardinia, where towns periodically switch off all non-essential lighting for Night of the Stars events. As artificial lights fade, the sky erupts with forgotten constellations, prompting gasps from residents seeing the Milky Way for the first time. These moments prove that beneath the glare, our cosmic inheritance still waits, as timeless as the photons that have crossed galaxies to reach us. The stars haven't gone anywhere, we've just forgotten how to see them. Long before telescopes or spectrometers, humanity's relationship with starlight was written in stories. The patterns we call constellations weren't just celestial maps, they were mythic tapestries, strung across the sky by cultures from the Polynesian navigators to the ancient Greeks. Orion the Hunter, prowling the winter sky, was a giant in one tradition, a celestial fisherman in another. The Pleiades, that shimmering star cluster, marked planting seasons for the Maya and served as ancestral guides for Aboriginal Australians. These weren't random tales. They were the first scientific models, attempts to explain and predict the cosmos using the only tools available: human imagination and the steady rhythm of the stars. That rhythm became humanity's first clock and compass. Saharan caravans followed the North Star across trackless dunes, its fixed position a beacon in the darkness. Polynesian voyagers memorized the rising and setting points of hundreds of stars, navigating thousands of kilometers across open ocean without instruments, a feat modern sailors still struggle to replicate. Even the pyramids of Giza align with uncanny precision to Orion's belt, their architects weaving celestial order into stone. Starlight didn't just illuminate the night, it shaped calendars, harvests, and empires, guiding civilizations as reliably as GPS guides us today. The transition from mythology to mathematics began with surprising grace. In 17th century Japan, poet-astronomer Shibukawa Shunkai corrected the imperial calendar by meticulously tracking star positions, blending art and science in a way that feels strikingly modern. Galileo's sketches of the moon, inked by candlelight, were as much works of Renaissance artistry as they were scientific revolution. This duality persists in modern astrophotography, where Hubble's iconic pillars of creation image isn't just data. It's a masterpiece, its vibrant hues revealing the birth of stars while stirring something primal in those who gaze upon it. Light's symbolic power transcends cultures. In Zoroastrianism, fire represents divine wisdom. In Hindu rituals, lamps dispel ignorance. In countless children's stories, a single star grants wishes. The Hubble Deep Field image showing thousands of galaxies in a patch of sky, no larger than a grain of sand held at arm's length, didn't just expand our cosmic horizons, it became a secular icon, a humbling reminder of our place in the universe. Science fiction, from Asimov to Arrival, often portrays alien communication through light patterns, echoing our deepest intuition that photons carry meaning beyond mere physics. Today, photons bridge disciplines in ways our ancestors couldn't fathom. Biomedical researchers use laser tweezers, essentially sculpted light, to manipulate individual cells. Quantum engineers entangle photons to create unhackable communication networks. Yet when we stand beneath a meteor shower or watch a solar eclipse, we're not so different from those early storytellers tracing shapes in the stars. The photons hitting our eyes still spark wonder, still whisper of mysteries beyond our grasp. Whether captured by a billion-dollar telescope or a child's first backyard telescope, starlight remains the universal language, connecting past to present, science to spirit, and Earth to the cosmos beyond. Deep inside the sun's core, where temperatures reach 15 million degrees and pressures could crush diamond into dust, two very different particles are born in the heart of nuclear fusion. Photons, the familiar particles of light, begin their slow crawl toward the surface, a journey that can take 50,000 years, as we've seen. But there's another, far more elusive particle created in these reactions, the neutrino. These ghostly subatomic specks, with barely a whisper of mass, don't tangle with matter the way photons do. The moment a neutrino forms, it streaks out of the sun at nearly the speed of light, escaping the solar interior in just over 2 seconds. That's the difference between mailing a letter through a crowded postal system and sending it by teleportation. This staggering speed gap turns neutrinos into cosmic messengers with unprecedented immediacy. When scientists detect solar neutrinos here on Earth, they're essentially peering directly into the sun's core as it exists right now, not the delayed photon-based snapshot showing conditions from millennia ago. It's like receiving a live video call from the sun's furnace while simultaneously studying a 50,000 year-old painting of the same scene. Together, these two perspectives create a stereoscopic view of stellar physics that neither could achieve alone. Detecting neutrinos, however, is no simple feat. These particles barely interact with ordinary matter. Trillions pass harmlessly through your body every second, leaving no trace. To catch even a handful, physicists build extraordinary detectors like Japan's Super Kamiok and a massive underground tank filled with 50,000 tons of ultra-pure water. When the rare neutrino does collide with an atomic nucleus in the water, it creates a faint flash of light called Cherenkov radiation, ethereal blue glow that sensitive photomultiplier tubes can spot. It's the subatomic equivalent of hearing a single snowflake land in a bustling city. The data from these shy particles has revolutionized our understanding of stars. Early neutrino detectors in the 1960s and 70s found far fewer solar neutrinos than predicted, a mystery dubbed the solar neutrino problem. The solution came with a stunning realization. Neutrinos change flavors as they travel, oscillating between three types that ordinary detectors couldn't all see. This discovery didn't just fix solar models. It revealed that neutrinos have mass, however slight, rewriting the standard model of particle physics. Photons and neutrinos, though radically different, now work in tandem to probe stellar secrets. When a neutrino burst from the sun aligns with photon observations, it confirms our theories about fusion rates and energy transport. During solar flares, neutrino spikes can arrive hours before the corresponding photon fireworks, offering potential early warnings for space weather that threatens satellites. Even supernovae become richer subjects for study. The neutrinos from 1987 reached Earth hours before the visible explosion, giving telescopes precious time to prepare. What makes this partnership so powerful is how each particle fills the other's blind spots. Photons show us surface details, sunspots, flares, the intricate dance of magnetic fields, while neutrinos provide unimpeachable proof of what's happening deep inside. Photons struggle to escape the sun's roiling plasma, but neutrinos breeze through as if it weren't there. Together, they've transformed astrophysics from a science of passive observation into something closer to interstellar medicine, where we can diagnose a star's internal health by combining surface symptoms with deep core biopsies. The next generation of neutrino detectors, like the Deep Underground Neutrino Experiment, promises even finer measurements, potentially revealing details about the sun's innermost structure that photons alone could never uncover. As these ghostly particles continue to whisper secrets from stellar cores, they remind us that the universe speaks in many voices. Some, like light, arrive in majestic waves we can see with our eyes. Others, like neutrinos, slip silently through the cracks of reality, waiting for us to build the right instruments to hear them. Hidden in the faint static between radio stations lies the most ancient signal in existence, the cosmic microwave background, or CMB. This whisper of microwave radiation is no ordinary light. It's the cooled remnant of the universe's fiery birth, a glow that's been traveling toward us for 13.8 billion years. Picture the cosmos not as the dark void we see today, but as a seething, opaque plasma, so dense that light couldn't travel more than a fraction of a millimeter before being swallowed by the hot soup of particles. Then, 380,000 years after the Big Bang, everything changed. As the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms, clearing the fog in a moment cosmologists call recombination. For the first time, photons broke free, streaming outward in all directions. Those primordial photons, once blazing with the heat of a young universe, have cooled to a mere 2.7 degrees above absolute zero, stretched by cosmic expansion from visible light into microwaves. What makes the CMB so revolutionary is how perfectly it preserves the universe's infancy. Tiny temperature fluctuations in this microwave globe, variations as small as 1 part in 100,000, revealed density differences in the early cosmos. These microscopic ripples became the seeds for all future structure. Slightly denser regions collapsed under gravity to form galaxies and clusters, while emptier zones stretched into cosmic voids. It's like discovering the blueprints for every city on Earth hidden in the grain of a single, weathered stone. When NASA COBE satellite first mapped these variations in 1992, scientists called it "seeing the face of God," not because it was mystical, but because it revealed the quantum fluctuations that birthed everything we know. Later missions WMAP and Planck refined these maps into exquisitely detailed snapshots, showing the universe's composition with staggering precision. The CMB confirms that ordinary matter, the stuff of stars, planets, and people, makes up less than 5% of the cosmos. Dark matter, which governs galaxy formation through gravity but emits no light, accounts for 27%. The remaining 68% is dark energy, the mysterious force accelerating cosmic expansion. These numbers aren't guesswork, they're etched into the CMB's patterns, calculated from the angles between temperature peaks like cosmic trigonometry. The CMB also carries echoes of the universe's earliest moments. Some theories suggest that during a period called inflation, space expanded faster than light itself in the first sliver of a second after the Big Bang. This hyper-stretching would have left gravitational wave imprints on the CMB's polarization, a smoking gun for inflation that experiments like BICEP and the Simons array continue hunting. Finding those patterns would be like uncovering fossilized ripples from the universe's first heartbeat. Perhaps most astonishing is how this relic radiation surrounds us completely. Every cubic centimeter of space, the air in your living room, the vacuum between stars holds about 400 CMB photons left over from the Big Bang. Your television's static contains a fraction of these ancient messengers, their energy diluted but still present after billions of years. They've outlasted the rise and fall of galaxies, the birth and death of countless stars, the formation of Earth itself. And when telescopes like the upcoming Light Bird mission analyze this light with even greater precision, we may uncover answers to questions we haven't even thought to ask yet about the universe's shape, its ultimate fate, or whether other universes exist beyond our own. For now, the CMB remains the closest thing we have to a time machine, carrying whispers from the dawn of everything directly to our instruments, and through them, to our understanding. Black holes twist the laws of physics into something unrecognizable, a place where light itself becomes a prisoner. Picture a beam of starlight venturing too close to one of these gravitational monsters. As it approaches the event horizon, that invisible point of no return, space-time curves so severely that all possible paths for the photon lead inward, like water spiraling down a drain. This is why black holes appear as perfect darkness at their cores, not because they don't emit light, but because any light that crosses the horizon can never escape to reach our eyes. Yet just outside this boundary, something extraordinary happens. Photons skim along the edge of oblivion, their trajectories bent into wild loops by the black hole's gravity. Some manage to break free after orbiting multiple times, while others get slingshotted into space, carrying distorted snapshots of the cosmic maelstrom behind them. The Event Horizon Telescope's groundbreaking image of the supermassive black hole in galaxy M87 revealed this drama in stunning detail: that glowing orange ring. It's not the event horizon itself, but light from superheated gas swirling around it. Photons caught in gravity's grip like fireflies trapped in a whirlwind. The dark center is the black hole's shadow, a region about 2.5 times larger than the actual event horizon, where light bends so sharply it creates a kind of optical illusion. This shadow isn't just absence, it's a silhouette of warped spacetime, a cosmic fingerprint proving Einstein's predictions about gravity's power to sculpt light itself. What makes this interplay between light and black holes so mind-bending is how it defies common sense. Normally, we think of light traveling in straight lines, but near a black hole, its path becomes a tangled scribble. Imagine standing beside one, and looking sideways you'd see the back of your own head. Because light from behind, you could loop all the way around the black hole and enter your eyes. This effect, called gravitational lensing, turns black holes into natural funhouse mirrors, amplifying and twisting the light of stars and galaxies behind them. Some distant galaxies appear as multiple smeared arcs around a foreground black hole, their images cloned and stretched like reflections in a broken mirror. Even more bizarre is what happens to light's energy in this chaotic environment. Photons falling toward a black hole gain energy, their wavelengths compressing into higher frequencies, a process called blueshift. Conversely, light escaping the hole's gravitational well loses energy, stretching into longer, redder wavelengths. If you were watching a star get shredded by a black hole's tidal forces, its final light show would start in visible colors before fading into infrared and then radio waves, like a cosmic sunset running in reverse. This energy theft isn't just theoretical. Astronomers have detected X-ray flashes from black hole accretion disks, the death cries of photons heated to millions of degrees as they spiral inward. But black holes don't just trap light, they also create it in unexpected ways. Jets of plasma shooting from their poles can outshine entire galaxies, powered by magnetic fields so intense they twist particles to near light speed. These jets often emit light in tight beams, like interstellar lighthouses visible across billions of light years. And in the strangest twist of all, quantum physics suggests black holes might slowly leak radiation Hawking radiation, a faint glow of particles born from the warping of spacetime itself. It's as if the universe refuses to let even these perfect traps exist in total darkness, insisting on one final glimmer against the void. The study of light's dance with black holes has rewritten our understanding of reality's limits. Each photon that escapes their grasp carries encrypted data about gravity's strongest possible grip, the geometry of warped space, and the violent physics of accretion disks. Future telescopes, like the planned Laser Interferometer Space Antenna, may even detect the ripples in spacetime from black hole collisions by how they subtly stretch and squeeze passing light. These invisible giants, once thought to be merely cosmic vacuum cleaners, have turned out to be some of the universe's most brilliant laboratories where light doesn't just die, but reveals the secrets of existence itself. Gamma-ray bursts are the universe's flashbulbs, blindingly bright, yet vanishingly brief cosmic explosions that outshine entire galaxies in the span of a heartbeat. Imagine a single event releasing more energy in 10 seconds than our sun will radiate across 10 billion years. That's the staggering power packed into these gamma-ray photons, the highest energy form of light, born from some of the most cataclysmic events since the Big Bang itself. When a massive star exhausts its nuclear fuel and collapses into a black hole, or when two ultra-dense neutron stars spiral together in a final, violent embrace, The resulting fireball unleashes twin jets of radiation moving at nearly the speed of light. If one of those jets happens to point toward Earth, we detect it as a gamma-ray burst, a fleeting but revelatory beacon from the edge of spacetime. These bursts come in two distinct flavors, each telling a different story of cosmic destruction. Long-duration GRBs, lasting from 2 seconds to several minutes, signal the death throes of massive stars in distant galaxies. Short bursts, flashing for less than 2 seconds, originate from the merger of neutron stars, events so violent they shake the fabric of spacetime, producing gravitational waves alongside their electromagnetic fireworks. The 2017 detection of GRB 170817 marked a watershed moment, as telescopes caught both the gamma-ray flash and the accompanying gravitational ripples from colliding neutron stars. This multi-messenger astronomy revealed something astonishing. Such collisions forge heavy elements like gold and platinum, scattering them across the cosmos in glowing clouds called kilonovae. Suddenly, the ring on your finger wasn't just jewelry. It was stardust forged in one of the universe's most extreme events. What makes GRBs invaluable to astronomers isn't just their violence, but their utility as cosmic yardsticks. Because their light travels through interstellar gas clouds before reaching us, absorption lines in their spectra act like fingerprints, revealing the composition and density of matter along their path. More remarkably, their extreme brightness makes them visible across nearly the entire observable universe. The most distant GRB ever recorded, GRB 090429, erupted just 630 million years after the Big Bang, its light carrying clues about the universe's chemical infancy, when the first stars were transforming primordial hydrogen into heavier elements. Yet capturing these bursts is a race against time. Satellites like NAS, Swift and Fermi telescopes scan the skies for gamma-ray flashes, then instantly relay coordinates to ground-based observatories. Within seconds, robotic telescopes swivel to catch the afterglow, a fading trail of X-rays, visible light, and radio waves that can reveal the burst's host galaxy and distance. This global scramble has uncovered surprising diversity in GRBs, some linked to supernova, others to mysterious, dark explosions with no visible aftermath, and a few so energetic they defy current physics. The record holder, GRB 22109A, unleashed a 5-minute blast so powerful it temporarily ionized Earth's upper atmosphere from 7.2 billion light-years away, proof that even across cosmic timescales, these explosions remain universe-shaping events. Beyond their scientific value, gamma-ray bursts pose a provocative question. Could one occur close enough to threaten Earth, while our galaxy lacks the frequent star formation needed to produce frequent long GRBs? A nearby burst could strip the ozone layer, triggering mass extinctions. Evidence suggests a GRB may have contributed to the Ordovician extinction 450 million years ago. Yet this cosmic peril also underscores life's rarity. Without the heavy elements forged in these explosions, planets like ours might never have formed. In the end, GRBs are more than just cosmic disasters. They're the universe's way of recycling matter on a grand scale, turning death into the raw materials for new stars, planets, and perhaps even life itself. Their photons, though fleeting, carry imprints of creation and destruction, written in the most energetic language the cosmos knows. The universe holds its secrets close, none more frustrating than dark matter, the invisible scaffolding that shapes galaxies yet refuses to interact with light. But photons, ever the cosmic detectives, have found ways to expose this elusive substance. Though dark matter neither emits nor absorbs light, its gravitational grip bends spacetime itself, warping the paths of passing photons like a lens carved from pure gravity. This phenomenon, gravitational lensing, turns entire galaxy clusters into natural magnifying glasses, their immense dark matter halos distorting the light of background galaxies into stretched arcs and ghostly rings. By meticulously mapping these distortions, astronomers have traced dark matter's invisible architecture, revealing vast filamentary webs spanning billions of light years. Some of the most striking evidence comes from collisions like the Bullet Cluster, where two galaxy clusters slammed through one another like ghosts passing in the night. Observations showed the visible gas detectable by its X-ray emissions slowed from the collision's friction, while the bulk of the mass, revealed by lensed starlight, sailed ahead unimpeded. This cosmic sleight of hand proved dark matter's existence beyond doubt. Something invisible was outweighing ordinary matter 5-1, and photons were the only witnesses. Intriguingly, light might reveal even more subtle dark matter interactions. Some theories predict certain dark matter particles could occasionally deflect or absorb photons through weakly interacting massive particles, or WIMP. Experiments like the Fermi Gamma Ray Space Telescope scan the skies for unexplained photon excesses, mysterious glows that could signal dark matter annihilations in distant galaxies. Other researchers hunt for faint distortions in the cosmic microwave background, the afterglow of the Big Bang, where dark matter's gravitational whispers might have left subtle imprints. Even starlight itself carries hidden clues. As photons traverse the Milky Way's halo thought to be thick with dark matter, some theories suggest they might interact with hypothetical dark matter particles called actions, causing their polarization to subtly rotate. Projects like the CERN Action Solar Telescope aim to catch this effect in action, turning the sun into a beacon that could illuminate dark matter's true nature. What makes these photon-based techniques so powerful is their versatility. From bending starlight to spectral anomalies, each unexpected twist in light's behavior offers a fresh angle on the invisible majority of our universe. Future telescopes like the Vera Rubin Observatory will map lensing distortions across billions of galaxies, while next-generation detectors may finally spot dark matter's fingerprints on individual photons. Until then, every flicker of starlight remains a potential messenger not just from luminous stars, but from the shadows that move them. The next leap in cosmic discovery is already taking shape, not in the stars themselves, but in the mirrors and sensors of revolutionary telescopes now being built. The Vera C. Rubin Observatory, poised to begin operations in Chile, will capture more photons in its first week than all previous optical telescopes combined. Its 8.4-meter mirror and 3,200 megapixel camera will scan the entire southern sky every few nights, creating a time-lapse movie of the universe on a scale never before attempted. This torrent of data, expected to reveal over 20 billion galaxies, will transform astronomy from a field of targeted observations into a dynamic hunt for cosmic anomalies. Imagine spotting a supernova in its earliest moments because your telescope photographs that patch of sky nightly, or tracking asteroids so faint they've slipped past every other survey. Rubin's real superpower lies in its ability to catch what no one thinks to look for: the unpredictable flickers and slow drifts that could rewrite our understanding of dark matter, stellar evolution, or even extraterrestrial megastructures. While Rubin sweeps the sky broadly, NASA-planned LUVOIR Space Telescope takes the opposite approach, peering deeper and sharper than any optical instrument before it. With a primary mirror up to 15 meters across, nearly 6 times Hubble's light-gathering area, LUVOIR could directly image Earth-sized exoplanets around nearby stars, analyzing their atmospheres for signs of life. Its coronagraph, a high-tech starlight blocker, will suppress a star's glare by a factor of 10 billion, like spotting a firefly next to a spotlight from thousands of miles away. The photons LUVOIR collects won't just show alien worlds, they'll carry detailed spectra that could reveal oxygen, methane, or even industrial pollutants in alien atmospheres. This isn't just an upgrade, it's the difference between seeing a pale blue dot and reading its chemical biography. Ground-based telescopes aren't standing still either. The extremely large telescope ELT, rising in Chile's Atacama Desert, will use 39-meter segmented mirrors paired with adaptive optics so precise they can correct for atmospheric turbulence in real time. Its lasers create artificial guide stars high in the atmosphere, allowing the system to counteract the twinkling that blurs ground-based observations. The result, images up to 16 times sharper than Hubble's, with light gathering power to study the first galaxies born after the cosmic dawn. ELT might even track the expansion of the universe in real time by watching how galaxy clusters slowly grow more distant over a human lifetime, a measurement so precise it could settle the debate over dark energy's true nature. The future isn't just about bigger mirrors, it's about smarter ways to combine them. Optical interferometry, which links multiple telescopes to act as one giant instrument, is overcoming limitations that once made it impractical for visible light. The Magdalena Ridge Observatory Interferometer in New Mexico can resolve details equivalent to spotting a dime on the moon's surface, while space-based concepts like NAS, a stellar imager, envision fleets of coordinated telescopes spanning kilometers. These arrays don't just amplify light, they decode its wave nature in ways single telescopes can't, revealing surface features on distant stars or the swirling gas around newborn black holes. Perhaps most exciting are the technologies we haven't yet imagined: photon counting detectors with zero noise, quantum entangled telescopes that surpass classical resolution limits, or even neutrino detectors that complement light-based observations. Each could open new chapters in cosmic discovery. The unifying theme is photons, collecting more of them, analyzing them more precisely, and extracting every possible clue about the universe's hidden workings. When Galileo first pointed his tiny optic tube at the heavens, he saw 4 moons around Jupiter, a revelation that shattered Earth's central place in the cosmos. Today's telescopes will make discoveries equally profound, not by replacing Starlight's ancient messages, but by learning to listen more closely than ever before. Photons are poised to transform not just how we observe the universe, but how we communicate across it. At the bleeding edge of this revolution lies quantum communication, where individual particles of light become uncrackable couriers for sensitive information. The key lies in a bizarre quantum property called entanglement, where 2 photons become mysteriously linked regardless of distance. Measure one entangled photon's polarization here on Earth, and its partner, whether orbiting Mars or drifting near Alpha Centauri, instantly assumes a corresponding state. This eerie connection, which Einstein famously dismissed as spooky action at a distance, has been experimentally verified across distances exceeding 1,200 kilometers via China's Mysteri satellite. This phenomenon isn't just a physics curiosity, it's the foundation for quantum key distribution, a cryptographic method where encryption keys are encoded in photon properties. Any attempt to intercept these keys collapses their quantum state, alerting both sender and receiver to eavesdropping. Unlike conventional encryption vulnerable to future quantum computers, photon-based systems offer theoretically perfect security. The European Quantum Communication Infrastructure Initiative already links government agencies across 30 countries with this technology, while startups like Quantum Exchange are building fiber optic networks protected by quantum keys. The interstellar potential is even more staggering. Traditional radio signals degrade over light years, requiring enormous power and slow data rates. But entangled photons could enable secure messaging between star systems without signal degradation, if we can maintain coherence across cosmic distances. NASA's Deep Space Quantum Link project explores this by testing quantum communication with the International Space Station, while theoretical designs for quantum repeater satellites could one day form a solar system-wide web. Imagine two spacecraft at opposite ends of the solar system sharing real-time navigation data via entangled photons, their connection unbroken by solar flares or planetary interference. What makes photon-based quantum communication extraordinary is how it turns Starlight's quantum quirks into practical tools. The same wave-particle duality that baffled early physicists now allows single photons to carry multiple bits of information simultaneously through superdense coding. Quantum teleportation, transferring quantum states between photons without physical travel, has already been demonstrated in labs using light's unique properties. These aren't incremental improvements to existing tech, they're paradigm shifts leveraging light's fundamental nature, yet challenges remain. Maintaining photon entanglement over astronomical distances requires overcoming decoherence from cosmic microwave background radiation and gravitational waves. Ground stations must detect single photons with near-perfect efficiency despite atmospheric distortion, but solutions are emerging: quantum memory devices that store photon states in atomic clouds, adaptive optics systems that compensate for atmospheric turbulence, and nano-satellites dedicated to quantum relays. Each breakthrough inches us closer to a future where secure interstellar communication isn't just possible, but routine. This convergence of quantum physics and information science proves Starlight's potential extends far beyond passive observation. The photons we've studied for millennia, once viewed merely as cosmic messengers, are revealing themselves as active participants in humanity's next communication revolution, one where the quantum and the cosmic intertwine. The night sky has always been humanity's shared canvas, a vast, open gallery where every culture has traced its myths, navigated its journeys, and pondered its place in the cosmos. But that canvas is now being repainted, not by nature, but by technology. Thousands of satellites from constellations like Starlink crisscross the heavens, their reflective surfaces catching sunlight long after dusk. What was once a pristine backdrop for astronomers and stargazers is becoming a flickering grid of man-made artifacts. The issue isn't just aesthetics, it's a collision between progress and preservation, where the very tools meant to connect us threaten to disconnect us from the stars. Consider the numbers. A single satellite megaconstellation can add tens of thousands of new moving points to the night sky, far outnumbering the roughly 6,000 stars visible to the naked eye. When these satellites pass through a telescope's field of view, they leave bright streaks that can obliterate delicate observations. A study from the Vera Rubin Observatory estimated that up to 30% of its images could be compromised by satellite trails once all planned constellations are deployed. That's like trying to study a Renaissance masterpiece while someone repeatedly flashes a strobe light across it. For astronomers hunting distant supernovae, tracking near-Earth asteroids, or mapping the cosmic web, these interruptions aren't just inconvenient. They could erase discoveries before they're even made. The cultural stakes run just as deep. For indigenous communities like the Maori or Navajo, specific stars and constellations are woven into language, ceremony, and oral history. The Pleiades, for instance, aren't just a pretty cluster. They are ancestors, guides, and timekeepers across multiple traditions. When artificial lights, whether from cities or satellites, drown out these celestial markers, they don't just dim the sky, they fray threads of cultural memory stretching back millennia. Even modern urban dwellers, often cut off from natural darkness, report a profound sense of loss when they realize their children might never experience the Milky Way as more than a faint smudge. Yet the debate isn't as simple as satellites versus stars. Global internet coverage promises to bridge digital divides, bringing education and economic opportunity to remote regions. During disasters, satellite networks can restore communication when ground systems fail. The challenge lies in balancing these benefits with protections for the night sky, a resource that belongs not to any corporation or country, but to every person on Earth. Some companies are already testing mitigations. SpaceX's DarkSat experiment used less reflective coatings, while newer designs angle solar panels to reduce glare. These efforts help, but with over 100,000 satellites projected to orbit by the decade's end, piecemeal solutions may not suffice. Legal frameworks haven't kept pace. Unlike terrestrial light pollution, which some cities regulate with shielded fixtures and curfews, space-based brightness exists in a gray zone. No international treaty explicitly limits reflectivity or orbital crowding. The Outer Space Treaty of 1967 declares space the province of all mankind, but offers no mechanisms to prevent one nation's satellites from eclipsing another's view of the cosmos. Proposals are emerging. The International Astronomical Union advocates for space sustainability standards, while the UN's Committee on the Peaceful Uses of Outer Space is exploring guidelines, but enforcement remains uncertain. What's needed is a shift in perspective, recognizing clear skies as a commons, like clean air or ocean fisheries, requiring collective stewardship. Some observatories now negotiate directly with satellite operators, sharing observation schedules to minimize conflicts. Citizen science projects like Satellite Streak Watcher crowdsource data to quantify the problem, and dark sky advocates are pushing for right to starlight principles that could shape future policies. The ethics here extend beyond astronomy. They ask whether humanity, in its rush to conquer new frontiers, will remember to preserve the awe that inspired the journey in the first place. Satellites may connect our digital world, but starlight connects us to something far older, a shared inheritance written in photons that have traveled longer than civilizations have existed. Protecting that connection isn't about rejecting progress. It's about ensuring that when we look up, we still see not just our own creations, but the universe that made us. Long before telescopes split starlight into spectra, philosophers saw in its glow something far beyond physics, a symbol of truth piercing the shadows of ignorance. Plato's cave allegory imagined prisoners mistaking flickering shadows for reality until one escaped into sunlight, discovering true forms beyond the cavern's dim projections. This ancient metaphor still resonates today, framing light not just as electromagnetic waves, but as the very essence of revelation. Modern science's quest to decode photons mirrors that allegorical journey. Each discovery, from Newton's prism to quantum duality, pulls back another layer of cosmic illusion, exposing realities stranger than fiction. The interplay between light and knowledge runs deeper than metaphor. Enlightenment thinkers like Newton and Goethe didn't just study optics, they wrestled with light's philosophical implications. Newton's experiments revealing light's composite nature shattered Aristotle's idea of pure, homogeneous illumination, suggesting even the most fundamental truths could harbor hidden complexity. Goethe, despite his flawed color theory, intuited something profound: that observing light requires acknowledging the observer's role, a precursor to quantum mechanics observer effect centuries later. These debates weren't just scientific, they were about how we perceive reality itself. Quantum physics injected new mystery into this ancient dialogue. When experiments proved photons could behave as both particles and waves, it forced a reckoning with the limits of human intuition. Bohr's complementarity principle, that light reveals different properties depending on how we measure it, echoes philosophical questions about whether reality exists independently of observation. The double-slit experiment, where photons seem to choose their nature based on experimental setup, feels less like physics and more like a Zen koan, challenging our very notions of objectivity. Starlight amplifies these questions across cosmic scales. Every photon from a distant supernova carries dual histories: the physical tale of its fiery birth and interstellar journey, and an epistemological saga, how its detection reshapes human understanding. When Hubble's observations of redshifted galaxies revealed an expanding universe, it didn't just add data, it transformed humanity's cosmic self-conception, displacing us from the center of a static cosmos to a fleeting speck in an evolving vastness. Contemporary thinkers like Carlo Rovelli bridge these realms, framing quantum photons as relational entities whose properties emerge through interaction, not isolation. This view mirrors Eastern philosophies where reality arises from interconnectedness, not independent objects. Meanwhile, dark energy's discovery, that the universe accelerates its expansion, reads like a metaphysical paradox. Invisible energy embedded in empty space itself drives cosmic dissolution, a concept as puzzling as any allegorical darkness. Yet for all its abstractions, light's philosophical power stems from visceral experience. Standing under a starry sky, feeling the pale glow of the Milky Way on your skin, you're literally bathed in ancient photons that have outlived civilizations. That tangible connection between retinal cells firing and distant suns dying grounds high-flung theories in embodied wonder. Photons become both messengers and metaphors, their physical journey mirroring humanity's halting progress from cave-bound ignorance to ever-expanding, if never complete, cosmic awareness. The light we study and the knowledge we seek remain intertwined, two sides of the same luminous coin, spinning through the void. As we stand beneath the infinite tapestry of the night sky, it's easy to forget that every shimmering point of light is a thread in a grand cosmic narrative, one written in the language of photons. These tiny particles of light do more than illuminate the darkness. They serve as the universe's oldest historians, carrying tales of celestial births, stellar explosions, and galaxies colliding in silent, slow-motion ballets. What humans once saw as mere pinpricks in a vast black canvas, we now recognize as dispatches from the front lines of cosmic evolution, each one a frozen moment in an epic that spans billions of years. Consider the sheer improbability of the journey these photons undertake. A single particle of light, forged in the heart of a star like Vega or Betelgeuse, fights its way through a chaotic plasma labyrinth for millennia before finally breaking free into the void. Then, it races unimpeded across light years only to be captured by the lens of a telescope, or even more astonishingly, by the retina of a human eye. In that final moment of detection, a journey older than civilization itself reaches its conclusion, converting ancient energy into a spark of perception. It's a chain of events so unlikely, so finely tuned, that it borders on the miraculous, and yet, this exchange happens countless times every second, weaving an unbroken connection between the cosmos and those who dare to look up. But Starlight's gifts go beyond poetry. Every wavelength, every spectral line, every subtle shift in polarization is a cipher waiting to be decoded. When astronomers analyze the light from a quasar, are 12 billion light-years away, they're not just measuring distance, they're reconstructing the universe's chemical adolescence, a time when the first heavy elements were being forged in the hearts of primordial stars. The faint microwave glow of the cosmic background radiation, that faded echo of the Big Bang, is more than a relic. It's the ultimate cold case file, holding clues about the universe's shape, composition, and ultimate fate. Even distortions in starlight, caused by invisible dark matter, map the hidden architecture of reality, revealing the unseen scaffolding that holds galaxies together. This relentless interrogation of photons has rewritten humanity's place in the cosmos. Not long ago, we believed Earth sat motionless at the universe's center. Then came Galileo's telescope, revealing moons orbiting Jupiter, proof that not everything revolved around us. Later, the redshift of distant galaxies shattered the illusion of a static universe, exposing a cosmos in explosive expansion. Today, telescopes like James Webb use infrared light to peer back to the universe's first chapters, while quantum experiments tease apart the spooky connections between entangled photons. Each advance feels like turning another page in a story that grows more astounding with every revelation. Yet for all our sophisticated instruments, the most profound magic of starlight remains its ability to stir something primal in us. There's a reason every human culture has woven stars into its myths, its navigation, its sense of time and meaning. Standing under a dark sky, watching the Milky Way stretch from horizon to horizon, we're participating in a ritual as old as consciousness itself. One that collapses the eons, connecting modern scientists with Bronze Age shepherds, all united by the same awe. This shared wonder is perhaps Starlight's greatest gift, a reminder that curiosity transcends eras, and that the universe speaks a language every one of us can begin to learn. So the next time darkness falls, step outside, let your eyes adjust. Trace the arc of Orion or the sprawl of Cygnus overhead. In that moment, you're not just an observer, you're the latest link in an unbroken chain of stargazers, each generation building on the last, all drawn by the same insatiable need to understand the light. Because every photon that finds you carries more than data. It carries an invitation to explore, to question, to never stop reaching.